This is the continuation of the video series about Soviet surface-to-air defense missile systems from Volkhov's Battleground channel. If you haven't seen the previous episodes of the series, check the links in the description. The videos about the S-25 Berkut and the SA-75 Dvina systems are essential to understand the content of the following episode. By knowing the composition and capabilities of the SA-75 Dvina missile battery, it is easier to explain and understand how and why the S-75 Desna and the S-75 Volkhov were different. Even before the SA-75 Dvina could stretch its muscles and fight in Vietnam, the development of another branch of the 75 product was in progress. Only 2 years after the first delivered Dvina system, the S-75 Desna, SA-2E, entered service in 1959. The S-75V Volkhov, SA-2E, came out in 1961. The S-75M Volkhov was next in 1964. In the Soviet Union, the S-75V and S-75M quickly replaced the Dvina, while in other countries the SA-75 Dvina remained operational for roughly 2 decades. The external difference between the Desna and the Dvina is marginal. The Desna was literally a Dvina, but it used the 6 cm wavelength and got some additional features that the other branch lacked. Even though the S-75 Desna and S-75V were short-lived systems, the S-75M Volkhov was definitive variant of this evolution line and quickly replaced the Desna. This S-75M Volkhov was used following the Vietnam conflict and the Middle East conflicts. The Desna was better suited against high-speed targets because of the improved fire control radar. Thanks to the shorter operational wavelength, the lobe of the antenna became narrower, which meant higher power density. Albeit the propagation loss is higher using 6 cm wavelength compared to the earlier 10 cm, the higher antenna gain compensated this. Another important change was the peak impulse power of the system had increased from 600 kilowatts to 1000 kilowatts. Combined, the plus 66% higher power and shorter wavelength resulted 33% higher detection range. The higher detection range provided more time to prepare and launch missiles against fast targets. If you wish to know more in detail about the radars and detection range, let me know in the comments. On the other hand, the scanned area of the radar was slightly smaller in wide beam mode compared to Dvina. Because of the shorter wavelength, the beam width was only 1 by 7 degrees. This meant the overlap scanned area was only 7 by 7 degrees, and not 10 by 10. Now let's speak about the most long-lasting variant of the SA-2 family. The most notable differences between the Volkhov and Dvina was the fire control radar. Another easily noticeable change was that the longer-range P-18 radar replaced the P-12 target acquisition radar. Besides this, there were many changes in the design that were not externally visible. The evolution line of the Volkhov got many features which the Dvina lacked and never received because that branch, at long term, was abandoned. Let's see the main differences one by one, starting with the fire control radar. The RSN-75 fire control radar of the Volkhov got 2 extra pair of parabolic antennas. Besides the external differences, the Volkhov used 6 cm wavelength, both the parabolic and wide beam antennas, as the Desna, which provided longer detection range. The power output of the Volkhov was the same as Desna's. The main parts of the fire control radar were as follows. P-12V, wide beam, elevation antenna. P-11V, wide beam, azimuth antenna. P-16, missile command transmitter antenna. P-14V, narrow beam, elevation antenna. P-13V, narrow beam, azimuth antenna. The reason for the introduction of the new pair of parabolic antennas was a new kind of target tracking mode which was called LoRo. LoRo means lobe on receive only. The Volkhov had the same wide beam mode as the Dvina when it used the P-12V and P-11V antennas, but with narrower scan zone. What was the point of the new antennas and the new modes? A more effective engagement of the high-speed targets. Remember this diagram from the first episode? When the development of the new SA-75 and S-75 started, only subsonic targets were in service, but it was almost as certain that supersonic targets would soon emerge as a threat. This prediction became true in the early 60s when the Mach 2-capable B-58 Hustler bomber entered service. Besides the man bomber, slower B-52 bombers started carrying the AGM-28 Hound Dog long-range missile, which also has Mach 2 traveling speed at 17 km altitude. The top of the high-speed category was the SR-71. The point of new antennas was to provide larger detection range, which ensured enough time for missile preparation and execution during the engagement process. The new pair of parabolic antennas provided a new kind of search mode. This new mode was the narrow beam search. In wide beam mode against a MiG-21 fighter-sized target, like the AGM-28 missile, the detection range was about 80 kilometers. The wide beam mode did not provide enough time for the missile preparation and engagement. In narrow beam search, the P-14V and P-13V antennas transmitted and received the reflection from the target. The SA-75 performed the search using data from P-18 target acquisition radar. The parabolic antennas transmitted with 1.7 by 1.7 degree pencil beam. Thanks to the narrower beam with the same 1000 kilowatts power provided 40% higher detection range. Against a fighter-sized target, detection range increased to 130 kilometers. Against bombers it increased from 115 kilometers to 150 kilometers. The center of the left, right and up-down scan path was moved along the edge of a circle. This resulted the crossed shape of the scanned area. One full elliptical scan took 9 seconds. This means a target traveling at Mach 3 flies a distance of 10 kilometers during a full scan. Even against such a high-speed target, the narrow beam search provided enough time advantage to perform an engagement. Using the narrow beam mode, the guidance of the missile was not possible because of the very narrow pencil beams. The missiles simply could not be tracked, and tracking is the foundation of the radio command guidance. Therefore, following the target detection, the fire control radar had to be switched to the LoRo mode. In LoRo mode, the P-14V and P-13V antennas illuminated the target, but P-12V and P-11V received the reflected waves from the target and radio beacon signals from the missiles. The missiles had to be within the overlapped area of scanned area of wide beam antennas to receive signals from their radio beacon. Following and establishing the tracking was done in narrow beam mode. As the target got closer, it switched to LoRo mode. This happened at about 95 kilometers distance against smaller targets. If the tracking was lost, it had to switch back to narrow beam and wait until the target got closer. When the system was in LoRo mode, the missile guidance became possible. The launch could be performed only using LoRo or wide beam mode. The LoRo mode provided several advantages over wide beam tracking. Not only the increased detection range, but in case of noise jamming, the burn-through distance was higher when the target appeared in the jamming band on the indicators. The LoRo mode was needed to overcome the angle detection jamming. Besides, the new antenna's additional circuit was needed to achieve that. Secondly, because the narrow beam was only 1.7 by 1.7 degrees wide, only the tracked aircraft's radar warning receiver detected the transmission of the fire control radar. Other aircraft could not unless they were very close to each other. At 30 kilometers tracking range, planes had to be within 450 meters of each other to be in the same pencil beam. As was mentioned in the previous episode, the aircraft carrying the AGM-45 had to fly inside at least one main lobe of the SA-75. In the Dvina's wide beam mode, this meant a 20 by 10 degree airspace. While in case of Volkhov and the LoRo, only 1.7 by 1.7 degree zone. The escorted planes could be protected by the planes carrying the AGM-45 only if they flew very close to the protected flights. This seriously restricted the engagement tactics and freedom of the SEAD escort planes. Of course, if Volkhov used the wide beam mode, it was more similar to Dvina with 20 by 7 degree scan zone. Despite the advantages, the LoRo mode still had some disadvantages as well. In Vietnam, the operators experienced that detection of the AGM-45 missile was possible during the launch separation. For moments, 2 target lens were visible on indicators in wide beam mode. While in LoRo mode, detecting such launch was barely possible because of the narrow pencil beams. So, although the LoRo made it much harder for the enemy to launch an AGM-45 strike against the SA-75, it was also more difficult for operators to spot the launch. This vulnerability was especially dangerous against the AGM-88 HARM, which could be launched with much larger aspect freedom compared to the AGM-45. But this is a later story. The AGM-88 was a weapon of the mid-80s and not the 60s era. The P-18 target acquisition radar could detect the anti-radiation missiles only from about 40 kilometers. Its refresh rate was lower compared to fire control radar because of the slower rotation of the antenna. Strong jamming could also block the P-18 or just reduce its detection range to a point which made it useless against the AGM-45 strike missile. Now we have mentioned the P-18, it is time to speak about it. The another easily detectable difference is the P-12 target acquisition radar, which was replaced by the longer range P-18. The radar had more antenna elements that transmitted a narrower beam. The output power increased from 180 kilowatts to 260 kilowatts compared to the P-12. Its nominal detection range against fighter was about 180 kilometers. The rotation speed was increased from 6 rpm to 10 rpm. The optical target tracking system was also different from Dvina. While the Dvina from 1969 had the manned doghouse, the Volkhov had the carrot television system. This did not require the two-man crew above the P-11V antenna. The carrot was shipped from 1983 with the S-75 M30P variant or installed during the overhaul of the earlier variants from 1984. The missile of the S-75 branch was also different compared to the SA-75. The liquid fuel rocket engine enabled controlled thrust, which further increased the maximal engagement zone of the missile. This made the missile especially effective against targets flying above 10 kilometers. The thrust characteristics depended on the elevation angle of the target before the launch. The thrust was 35 kilonewtons for 45 seconds if the elevation was smaller than 24 degrees before the launch. The thrust was 35 kilonewtons for 24 seconds, then was lowered to 20 kilonewtons for 55 seconds if elevation was higher than 24 degrees. Tactical fighters usually approached from below 24 degrees in elevation. Another perk besides the controllable thrust was the 35 kilonewtons maximum thrust. This extra thrust meant a 12% increase compared to the missiles of the Dvina. These changes increased the kinematic range of the missile at low altitude by about 15%, and at medium-high altitude, about 30%. This engine upgrade was not available to the first missile variant. The S-75 Desna used very similar missiles to what the SA-75 Dvina had. The main difference was that the missile transponder beacon used the 6 cm wavelength instead of 10 cm. The V750VN13D essentially was a V750V11D, just it was compatible with the Desna. The missiles of the Volkhov got very similar or the same upgrades in features as the Dvina benefited from. The first missile was the V750VN13D. It had 2 minutes preparation time and could be kept in ready-to-launch state for 30 minutes with 27 kilometers range. The minimal engagement range was 5 kilometers. This early variant lacked the selectable and increased thrust engine. The next missile generation was the V755-20D, which had many subvariants, each representing a capability upgrade. The V755-20D had 43 kilometers range and 300 meters minimal engagement altitude thanks to upgrade on the proximity fuse. The V755-20DA had increased engagement altitude against slow-flying spy balloons. It was increased to 35 kilometers. The V755P-20DP could utilize the passive phase of the missile following the engine burnout. Against non-maneuvering subsonic targets, the engagement range increased to 56 kilometers. The V755S-20DS, thanks to the new 5E11 type proximity fuse, had an even lower 100-meter minimal engagement altitude. The V755SU-20DSU got the upgraded gyroscope. The spin-up time in the missiles was reduced from 2 minutes to 30 seconds, but the time to keep gyroscopes spinning without overheating was decreased from 25 minutes to 5 minutes. The V755U-20DU missile variant got every upgrade except selective radio proximity fuse. The V579-23D5U-23 represented the third missile generation for the S-75M Volkhov. These missiles were newly built, not upgraded ones. They had all the features of the best missile while the maneuverability was increased. Below 10 kilometers the maximum achievable G overload was 9 G instead the 6.5 G of previous missiles. The V750 and the V755 missile variants had a 196 kg warhead which contained 8,200 fragments. The V759 had a bit larger, its weight was 201 kilograms while it had 29,000 smaller fragments. The engagement zone of the Volkhov was similar to Dvina. The zone grew larger thanks to the new engine with increased and selectable thrust. Of course, against fast and high-flying targets, the 6 cm SNR-75 fire control radar made it possible to utilize the better kinematics of the missiles. The presented engagement zones are considered with the V755-20D and later missiles for the Volkhov system. The more maneuverable V759 missile below 10 km has about 10% shorter range than the V755 had. The S-75 Desna with V-750 VN-13D missile had the same engagement zone as the SA-75 Dvina with the V-750 V-11D. This engagement zone has been presented in the previous episode, check the link in the description. The maximal engagement distance is 56 km at 20 km altitude. At low level, because of the dense atmosphere, the maximum range is shorter. Below 1 km altitude the range is 24 km, and at 5 km altitude the range is 40 km. The minimal distance is 7 km. The minimal engagement altitude is 300 meters. Following the V-755 U-20D Su missile, the minimal altitude was reduced to 100 meters thanks to the new 5E11 type proximity fuse. Maximal altitude against a target up to 300 meters per second speed is 30 kilometers, but in this case the maximal range is only 45 kilometers. The maximal flyby distance against incoming targets is 42 kilometers, against receding targets it is 35 kilometers. The engagement zones include the passive phase of the missile with burned out engine. The passive phase starts at 33 kilometers range with 10 kilometers altitude, and at 43 kilometers range with 20 kilometers altitude. The dashed line shows the engagement zone using 3-point guidance mode against slow balloons. The US used spy balloons in Project Genetrix to make photos of the Soviet Union. The maximal engagement altitude was higher because target speed was low, and the missile did not have to make hard turns. The engagement zone against faster targets became smaller as the speed increased. The engagement zone targets up to 420 meters per second, roughly Mach 1.5, is smaller because the passive phase of the missile is not considered anymore. The maximal engagement distance is 43 kilometers at 20 kilometers altitude and even less at the typical altitude of fighter planes. Mach 1.5 speed by a manned plane below 10 kilometers is impossible because of range issues for any plane. With the more maneuverable V-759 missile the engagement range was about 1 to 3 kilometers shorter depending on the target altitude. Firing on a receding target traveling above 420 meters per second was not possible. The maximal engagement range was the same 43 kilometers as in the previous case, but the extent of the zone is considerably smaller. Targets with larger than plus or minus 70 degrees in azimuth could not be engaged. With the more maneuverable V-759 missile the engagement range was about 1 to 3 kilometers shorter depending on the target altitude. Between 640 meters per second and 1000 meters per second target speed, the maximal minimal engagement distance was between 16 kilometers and 35 kilometers depending on altitude. The flyby distance was less than 25 kilometers and the azimuth had to be smaller than plus or minus 50 degrees. The maximal engagement range reduced to 40 kilometers at high altitude. Against high-speed targets it was impossible to launch more than 3 missiles, 1 full salvo, because of the short time that a target spent in the engagement zone. The maximal target speed until the S-75V variant was 640 meters per second. The S-75M had the upgraded fire control radar which made it possible to track targets up to 1000 meters per second. The S-75 also could be deployed in the same way as the Dvina on field, but another typical deployment method was using fortified battery posts for the cabins and vans the system. Of course, the radars could not be sheltered but the cabins could be protected. In case of attack the chance of survival for the crew was higher which may have a positive impact on the morale. The composition of a Dvina, a Desna and a Volkhov missile battery was very similar. They had the same quantity of missiles and radars, only their types were different. The auxiliary equipment also was very similar. Now that we know the main physical and external differences, it is time to speak of some other features of the S-75 branch and its evolution timeline. When the first S-75 Desna, SA-2E, were deployed in 1959, they already had the SDC radar mode which made it possible to intercept low-flying targets and ground clutter. If the target was flying at very low altitude, the ground clutter could make the target acquisition difficult because the ground also created a reflection just as the target. The SDC radar mode utilized a feature of the coherent pulse radar transmission. This means that the transmitted sinus wave was always transmitting with the same phase. In case 2 consecutive impulses had been transmitted with a different phase the SDC mode would not have been possible. This makes it possible to subtract 2 consecutive target reflections from each other. The SDC using the Doppler phase shift of the moving targets could differentiate between the moving and stationary targets. On left side are indicators, elevation and azimuth, with ground clutter reflections. On right side are the indicators in case SDC filter is applied. The ground clutter does not disappear completely, but at least manual target tracking was possible. This means that a target with 0 radial speed also remained visible though they were faint on the screen. The Dvina never received this upgrade because its SA-75 radar was not able to transmit coherent waves. The SDC is called MTI, moving target indication by the Western terminology. The SDC mode also could be used to filter the chaff. Following the chaff drop, the chaff cloud decelerates and it moves roughly with the speed of the wind. Therefore, the SDC mode got the feature of the wind compensation. In this case, chaff moving at certain speeds were filtered. The ground clutter filtering was not possible. Fielding of the S-75V Volkhov started in 1961. It got the pair of new parabolic antennas which made possible for engagement on Mach 2 targets thanks to the larger tracking range of the Loro. In 1964, the S-75M1 Volkhov, which was able to use nuclear warhead-tipped missiles, entered service. The first of its kind was the V-760-15D missile, which later was replaced by the V-760V-15D V5U-29. The latter had a bit better maneuverability. It could reach 6.5 G below 10 km, while the previous type was only 5.8 G capable. To ensure the guidance in case of strong jamming, the S-75M1 got an additional decimeter wavelength RD-75 Amazonka range-finding radar. That provided a secondary range tracking option. This ensured the detonation of the nuclear warhead in the right moment. Nuclear warheads never were exported outside of the Soviet Union, but interestingly the radar was, but only to Romania. The passive phase of the missiles could be utilized from the S-75M1 variant with the V-755 P-20DP and the nuclear-tipped 15DP missiles. Both were fielded from 1964. In 1971, the 5U-23 missiles with increased maneuverability and the S-75M2 upgrade was delivered thanks to the experience of Vietnam. Compared to previous 6.5 G maximal overload, the new missile was capable of reaching 9 G below 10 km altitude. In 1975, the S-75M3 was deployed. This type received the ECCM, Electronic Countermeasure, GSV system, additional electronics, against angle deception jamming. The GSV and SDC modes could not be used at the same time, and GSV required the Loro mode. The base principle of the GSV was using different beamwidth antennas to filter out the effect of the angle deception jamming. In 1978, the testing of new S-75M4 and development of the S-75M5 was in progress. In parallel, state acceptance of the first S-300 PT Berkut SA-10A Grumble system. Because the successful state acceptance and started deployment of the S-300 PT around Moscow, all further development work on the S-75M4 and S-75M5 was immediately stopped. Even though the M4 upgrade project was cancelled, the already developed new items were made available as an upgrade package. This became the S-75M3OP variant, which was fielded in 1983. It utilized the 9S33 A electro-optical television target tracking system. The field of view of the TV system was selectable at 2 degrees or 6 degrees. The resolution was 840 by 600 pixels with 25 frames per second refresh rate. Against fighter-sized targets, the tracking distance could be about 20 to 25 kilometers. The new upgrades were built during the scheduled deep-level maintenance, which happened every 5 years. At the end of '80s. In theory, all Volkhov systems were on S-75M3OP configuration. In 1988, the last exported S-75M Volkhov was delivered to Romania. The SA-75 Dvina system was replaced with Volkhov from mid-70s and early 80s in Warsaw Pact, and also Third World countries. The Volkhov was exported in 2 larger waves. The first lasted from 1964 to early 70s, the second happened from late 70s to 1987s, when in the Soviet Union the S-300 PT and S-300 PS started to replace the S-75M missiles batteries. Following the end of Cold War, most of operators phased out the remaining S-75s. The reason was not only their capabilities and age. In 1992, the newly formed Russian Federation declared that support of the old Soviet analog SAM systems, the SA-2, 3, 5, 6 and 8, would end on February 1993. Following this declaration, every operator had to rely on their own spare parts inventory and cannibalization of the existing systems. This made it possible to expand the service life, but eventually it led to less and less active units. Many countries retired the older SAMs even before the 21st century. Russia retired the last Volkhov battery in 1996 following the delivery of the S-300 PM Volkhov M6M, SA-2E systems. After about 4 decades of service of SA-2 family in Russia ended. If you like the video, share, subscribe and follow the channel. Further videos are coming soon, not only about air defense systems but also about military operations and many other topics.